Thank you, Non. Thank you a lot to the organizers, to Wendy, to Peter. It's a pleasure to give a talk in honor of Michel and his mathematics. So this is a joint work with Benjamin Hennion from Orsay and with Valerio Melani from Florence. So the plan is the one that you see there. So the first thing I will recall what is Beilinson-Drinfeld Grassmannian. Then we will need some higher dimensional analogs of Bovill-Laszlo theorem. So this is formal gluing and flag decomposition for the stack of G bundles. Then I will introduce the flags, so nonlinear flags. When you go on a surface, you can consider not only divisors, but also points on the divisor. So this gives what I call a nonlinear flags. And I will describe the structure that we will put on these objects. And finally, we'll introduce this flag version of Beilinson-Drinfeld Grassmannian. I would like to keep some time to speak about further directions at the end. So I hope I managed to do it. So let me recall this Beilinson-Drinfeld Grassmannian. So fix let's say projective smooth algebraic curve over C, georeductive algebraic group over C. Then we first introduced they first introduced the run space, which is this pre-sheaf on schemes over C, which assigns to any scheme over C the finite the set of finite non-empty sets of points in C, as points in C. This is just a pre-sheaf. I mean, it's, for example, it's not even an étal sheaf, so it's important to keep it as a pre-sheaf. Then the Grassmannian, the Beilinson-Drinfeld Grassmannian in its so-called run version is the following thing. So again, it's a pre-sheaf of sets. This sends a test scheme S to the set of triples where X is an element in the run C of S. So it means that X, underline X, is just a finite non-empty bunch of points as points in C. E is a G bundle on the product, C times S, and phi is a trivialization of E outside the graph, the joint graph of underline X. So there is an obvious projection map from the Grassmannian to the run space where you just forget E and phi. And note that, I don't know how to move this. I cannot move the. So the fiber of this map from the Grassmannian to run space at some point X is just, you can write it as this fiber product of group points, but it turns out that it's actually a set. So the map from the point, so spec C to bun G of C times S minus the graph is just given by the trivial bundle. Oh, sorry. So there is a that you can take union of points. So this gives a semi-group structure on run C, which is non-unital, because remember we have supposed that the finite subsets of points are non-empty. So it's a semi-group structure. And we define the disjoint part of the product of run C, which is just what is written there. So pairs of points which are disjoint. Then this Grassmannian, this Beilinson-Drinfeld Grassmannian, I mean, the reason why it's important, one of the reasons why it's important is that it satisfies the so-called factorization property. And the factorization property can be spelled out in the following diagram, saying that, so for example, you have, let's start from the right. You have the projection P from the Grassmannian to run C at the extreme right. And then you can take the union restricted to the disjoint pairs of points. So this gives you the first leg. And you can take the pullback of this diagram and you obtain something. You can also consider on the extreme left, you can consider the inclusion of the disjoint part of run C times run C to the full run C times run C. And you can consider the projection from the product of the Grassmannian with itself. So this projection is not written down, but it's P times P. Okay, and you have a diagram, you can take a pullback of that. And the factorization property can be stated by saying that there is a canonical map between these two pullbacks, and this canonical map is an isomorphism. And moreover, this factorization isomorphism between the two pullbacks is compatible with the trivial bundle section, which goes from, sorry, this should be run from run C to the Grassmannian, so it's wrong. It's not one G, but it's run C, and satisfies a suitable cocycle condition when you take disjoint triples of points. Okay. Now we start saying, we start going in the direction of generalizing this construction to surfaces, where we replace the curve C with a surface. So we need a formal gluing result, which is the analog of Beauville-Laszlo result that is used in geometric Lagrange on a curve. So, for example, for the Beilinson-Drinfeld Grassmannian, and it's due to many people, which some of them are listed there. So in the same setting as before, but X can be any Noetherian scheme, locally Noetherian scheme, and you take a closed subscheme, then you have a map from the stack of G bundles on X to the stack of G bundles on X times minus Z, so on the open complement, times the stack of G bundles on the formal neighborhood of Z, and which are compatible on the puncture formal neighborhood, which is Z hat minus Z. And the restriction map is an equivalence of stacks. That's formal gluing in this general form. But beware that below, I mean, the band G of Z hat minus Z, so the puncture formal neighborhood of Z, has to be defined properly, because, I mean, if you take Z hat as a formal scheme, then Z hat minus Z is empty, so it doesn't make sense, right? So one way out is that we consider the affinization of this. So we say that Z hat minus Z applied to some spec A is just spec, not formal spectrum, but spectrum of the formal completion of A at the ideal IZ minus the closed Z, which is spec A mod IZ. And some remarks on this formal gluing result is that, of course, only the reduced subscheme of Z matters, because both Z hat and these affinizations Z hat minus Z are insensitive to the scheme structure. And by algebraization, one can also replace the Z hat, which is on the left, on the extreme right of the formal gluing isomorphism, with the Z hat affine, which is defined, as you may imagine, as is written there. because then bun G on Z hat and bun G on Z hat affine are the same. I mean, this is a result. It's not totally obvious. And if one has another closed subscheme of Z, one can further decompose bun G of Z hat along using the closed Z prime in Z hat. So we have a flag decomposition along flags of arbitrary length, flags of closed subschemes. And I mean, we will not use this here, but formal gluing also works when X is a derived stack, so it's a stack. Okay, from curves to surfaces. So I wanted to list here at least the references I have read and I try to understand. So probably there are more references to give, but I will stick to those. So I guess the first attempt to extend some kind of Langlands program to algebraic surfaces is this paper by Kaplanov, Ginsburg, and Valerio in '95. And in the same year, there is this beautiful paper by Kaplanov on the analogies between the Langlands correspondence and TQFT, where especially he uses higher local fields. And I wanted also to list also this book by Beilinson-Drinfeld scalar algebras from 2004, just because there is a comment. I mean, the book is a wonderful book, but the thing that interested us was this comment in 3.4.6 that I mean, usually the way I described it before, the Beilinson-Drinfeld Grassmannian used the run space, okay, which is in some sense is a bad object because it's not even a sheaf in the topology. So, but they remarked that you can use Cartier divisor on the curve instead of the run space, and you can do it in two ways. I guess there was a first version and the second version. The published version is where you consider the Cartier divisor up to this reduced equivalence relation, which is written there. I say that D and D prime are equivalent if they have the same underlying closed space, or even you don't impose these reduced equivalence, but when you study objects on this space like sheaves, so they want to define factorization algebras in that book, they are insensitive to the underlying scheme structure of the device. So particularly if you have a sheaf F, you say that F on D is equal to F on D prime whenever D red is equal to D prime red. But this is just a remark. They say that, I guess they prove also that the definition of factorization algebra, so as sheaves, it's the same as the definition used in the run space or Cartier divisor. They are the same, but they don't pursue this thing. So, but when I saw this, actually, it was together with Mauro Porta, we saw this remark, and then we say, okay, maybe we can do it on, try to see what's going on surface, because on a surface, okay, you can consider Cartier divisor, and you can also consider subschemes of the Cartier divisor, so a flag of the type D, Z, where Z is included in D. So let me first introduce these objects. So we fix X now is a smooth projective surface over C. Then flag X is this pre-sheaf of posets on the Noetherian affine schemes over C, which as objects, flag X of some affine Noetherian over C, flag X of S, the objects are paired, DZ, where D is a relative effective Cartier divisor in X times S over S, so it's flat over S in particular. And Z is like a family of points, so is in yield well, I put less than or equal to 0 because I can allow Z to be empty. I want to allow Z to be empty. And the condition is that it's nested. So this pair is nested. So Z is inside D. And the morphisms are defined this way. So there is an obvious notion of inclusions between two pairs like this, DZ and D prime Z prime. And so the inclusion is just this diagram, which is displayed there, commutative diagram. But we require that not exactly that Z is the pullback of this diagram. So the smallest set of points is the pullback of the rest of the diagram, but that it's an isomorphism on the reduced part. Okay, so these are morphisms. Of course, this forms flag X of S is a poset here, because these maps are all closed immersion. Yes. Then we want to consider, remember, on the run space, we had the run space, then we have the run space times the run space, maybe disjoint, and we want to take the union. So we want to define like something like run times run disjoint, but in a way, in an algebraic way, so that the union makes sense. Okay, so we do like this. So flag X at level 2. So it's just the full subcategory of flag X times itself. And you just take the object D1, Z1, and D2, Z2, such that there are two conditions here, that the intersection of the Cartier divisor part is a relative effective Cartier divisor in D1 and D2. And we require that the intersection of D1 and D2, which contains, of course, the intersection of Z1 and Z2, is actually equal to that as schemes. Okay. So, for example, take the two axes, x and x equal to 0 and y equal to 0. Then this is so this transversal properties is included in this case, because then the intersection of the two axes, so the origin is not a Cartier divisor in the sum of the two divisors, in the union of the two divisors, but it's a Cartier divisor in each one of the two. And then we can, with these conditions, we can define the union of these good pairs of flags, which is just what you expect, what you would like to do in general. So the union of these D1, Z1, and D2, Z2 is just the sum at the Cartier divisor part, and the union at the point, so ILB0 part. So one remark here is that this union is well defined, because once you have this second condition of good pairs of flags, so Z1 intersected with Z2 is D1 intersected with D2, and you know that D1 intersected with D2 is a relative effective Cartier divisor, this intersection is flat over S. So in particular, Z1 intersected with Z2 is flat over S. And then the union, if you have two subschemes which are flat over S, and you know that the intersection is flat over S, then the union is flat over S, because in general, this is not true. So that's one of the reasons why we added this condition. And note also that the sum of the Cartier divisor under this, the first condition in the definition of good pairs is the same as the union. So you can define the union of subschemes or the sum of Cartier divisor, and they are the same as schemes. Okay, so you can think about these good pairs being like transversal in good position, or transversal, but what is the precise definition is the one I gave it here. So we want to go on, so to construct a simplicial object. So we observe that once we have whenever we have a partial monoid, so the operation, the monoid operation is only partially defined, so it's defined on a subset of M times M. Then there is an associated simplicial object, which is a classifying space, if you want, the classifying simplicial object, which is, so for example, at level 0, we take what is the initial object, then we take M at level 1, and at level 2 we have this M2, which is a subset where mu is defined, and of course, I mean, I wrote it wrongly. So there are two projections from M2 to M, PR1 and PR2, and then there is the thing that I denoted as the union, but it's wrong. It's just mu. Okay, it will be the union in our case, but it's just mu here in the general case. And this BM can be seen as a co-skeletal extension, two co-skeletal extension of the diagram, which is written there, just the first 3 levels of the simplicial object. So we do the same here with this partially defined union, and we define flag X bullet as this co-skeletal extension. This is an object, the simplicial object in functors from Noetherian schemes over C2 posets. Okay, this is a simplicial object, and then what we prove is that this simplicial object is actually a two-seagull object in the category where it lives. And so two-seagull object, I'm pretty sure that it was already mentioned in this conference. And but anyway, you can see that a two-seagull object as an algebra object in correspondence. Okay, this point of view is will be useful later. So about the proof, so on morphisms, this thing is easy because there are maps of posets, so they are easy to handle. And for objects, the goodness condition basically ensure that it's true. You have to check some things, especially you have to check that flatness is preserved, but this can be done. So in our analogy, flag X bullet, this simplicial object will play the role of run C, of the run space of the curve, where X now is a surface. But if you remember the remark I mentioned by Belinson-Drinfeld, if you pass to, you can say, I want to pass to reduced equivalence relation, which is the obvious one you can imagine. But then the simplicial object you get is no more two-seagull. Okay. So that's basically because taking quotient taking quotient is a colimit, but the two-seagull condition is a limit condition, and they don't go well together in general. And in this case, they don't. In any case, what we will prove is that the Grassmannian we will build over this flag X bullet will have a flat connection. So this is probably an obscure remark now, but I hope to make it clearer later. Okay. So in the sense that what the object we will construct over this flag X bullet will be topological in some sense. So they will not see the difference between a pair DZ and a pair D prime Z prime if the two are reduced equivalent. So what's this Grassmannian that we construct over a flag? So first we fix a flag and we define an object, and then we will integrate over all the flags by using a Grothendieck construction. So let's start with the first step. And so for a scheme Y and a nested closed subscheme Z dy in Y, then we define this stack over Y, which is so it classifies bundles on Y together with the trivialization on Y minus D, so on the open part of the complement of the Cartier divisor, a trivialization on formal completion of Z, And this two trivialization has to be compatible on the intersection. Not that the intersection makes sense because we are only considering z hat affine. So if you consider y minus d intersected in y with z hat, formal completion as a formal scheme, as an in scheme, it's empty. But if you consider z hat affine, then it's not. So we require that these two trivializations on y minus d and z hat are compatible on their intersections. And not also that since, I mean, this definition makes sense even if d is not a Cartier divisor, okay? But if, as in our case of interest, this d is a Cartier divisor, then y minus d is quasi-compact and schematically dense. So one can prove that this stack over y is actually a sheaf of sets for the flat topology. Sets, okay, so it's, okay, there is no stacky part. And then as in, I didn't mention this at the beginning, but even the Beilinson-Drinfeld Grassmannian has there is a local version and a global version, and these two versions are isomorphic, and even in our case this is true. So it's stated there. So the Grassmannian that I defined before at the beginning of the slides is the same as its local version, where you basically replace y with d hat, the formal completion of d inside y. And this is the analog, yeah, this is already something I saw. And this isomorphism uses the formal gluing, okay? And in the curve case, it used the Bouville-Laszlo, which is formal gluing for curves. So now this was defined for a fixed flag, and I want to integrate over all the flags. So the procedure is rather formal. I just summarize it here. So if you fix a test scheme, then you have a functor which are denoted by gr x of s, which goes from flags x of s to sheaves over x times s, which just take a flag and associated to it the Grassmannian of x times s with respect to d and z, the flag d and z. This is a sheaf. You can take global section, and this is what I call big GR x of s. And then, and this is a functor from flag x s to sets. And then you take the Grothendieck construction of this. So you get a functor from affine Noetherian over C to posets, and you get also an obvious natural transformation Q from this gr of x to flag of x. So in more concrete terms, curly Grassmannian of x. So this will be the flag Grassmannian of x, evaluated on S, classifies pairs F and E, where F is a flag on x times S, and E is a global section of the Grassmannian at the flags F. So it means that this underlying E is a bundle on x times S together with compatible trivialization on x times S minus D and on Z hat. And this is an important remark or proposition or result, that if you, now this flag Grassmannian is, it has values in posets, okay? But now you can forget about the partial order. So you can forget about the inclusions of flags and just go to sets. So you get a pre-sheaves on affine Noetherian over C, as pre-sheaves of sets. And then this pre-sheaf of set, you can prove it's represented by an int scheme. And this is related to a paper by Herrero, Alper Leinster, and another co-author that I forgot. Sorry. So we use their result to prove this result. They only consider but they work in a different setting. But let's say for G equal to GLN, the two things are comparable, but they work only with flags of the type D empty set. So only the Cartier divisor is considered. So, and then you get, if you only consider those kind of flags, you get actually a quasi-projective in scheme. But when you consider also Z hat, then you get something which is, if you want, still quasi-projective, but of infinite type. So I just say it's an in scheme in general of infinite type. I mentioned the flat connection, and this is how it goes. So you can, once you have, now again, we fix a flag, and Y will be X times S in our functorial construction, and DZ is a flag in Y. Then we have the Grassmannian, which is defined like this. And you can also consider the Grassmannian of the reduced flag. I mean, if you work in families and you have DZ, which is a flag, so in particular it's flat over the base S, then the reduced parties would not be flat in general. So this is just the definition. This is why I put a definition there. So, but it's the same definition. So it's GRU with respect to D reduced, Z reduced is bundled on Y, which would have a two trivialization, one on the complement of D red, one on Z red hat, which is the same thing as Z hat, and which are compatible on their intersections. And then this observation, which is pretty obvious, this topological invariance, together with the fact that C is a perfect field, implies that there exists a canonical Grothendieck-Fleck connection on the map that goes from the Grassmannian and forgets to the flag part. I just wrote down what a Grothendieck connection is in this case. So this might explain the probably obscure remark I made at the beginning, that that in this precise sense, the flag Grassmannian of X doesn't depend on the scheme structure. So only depends on the underlying topological spaces of the flags. And this is also a feature that the affine Grassmannian has. I mean, the fact that it exists a canonical flat connection in the curve case. So it's we are basically recovering many of the known results in the curve case for surfaces with this new definition. So we have a map. Sorry, I go back. So we have a map from the Grassmannian, flag Grassmannian to flag of X, but flag of X is a simplicial object, and it's useful to consider it as a simplicial object because we can consider the union of flags. Then what we want to do is to extend the Grassmannian of X, flag Grassmannian of X, to a full simplicial object. So we do it like this. So we define, so we take the map Q, which goes from the Grassmannian of X to flag of X, which forgets the bundles and keep only the flags. Then we have the union operation on the flags, defined only for pairs of good flags. And then we take the pullback. And the map from the pullback, we call it GR X2. And the map, the horizontal map, we call it delta 1 for an obvious reason. And so with this definition, maybe it's not completely obvious, but if you have GRX2 and you evaluate on S, this classifies tuples F1, F2, and E, where F1, F2 are flags, good pairs of flags, and E is an element in the global section of the Grassmannian with respect to the union of the flags. Okay, that's because of this union here. So there is this theorem which is not so easy to prove, and but the fact is that remember that we have defined GRX2 by using the map Q and the union map from flag X2 and to flag X. But of course, I mean, you can consider from flag X2 to flag of X, you can consider the obvious projection, right? Projection on the first flag and projection on the second flag. So these are D0 and D2. And the point is that it's not clear that it exists. There exists two map delta 0 and delta 2 from GRX2 defined as the pullback using the union, so that using D1 delta 1 to GR of X, such that this diagram commutes. But the fact is that there is a commutative diagram like this, and the proof boils down to building up to functoriality projection maps from the Grassmannian of the union of two flags to the Grassmannian of the constituent flags. And you need a formal gluing applied to puncture formal neighborhoods and special care with dealing with the affine completion. So I'm not claiming it's a super difficult result, but it's not obvious. And here is an idea of the proof, but maybe I will skip it. So maybe later I want to discuss the directions. So now we have this first chunk of the simplicial object, which is GRX2, GRX, and the point, and we have the obvious maps, no? Delta 0, delta 1, and delta 2, where delta 1 is the one defined through the union, and delta 0 and delta 2 are the one defined through the projections. And we can extend this, even this result of extending, it's not completely obvious, but one can do it. You can extend this to a simplicial object together with the simplicial map from GRX bullet to flag X bullet. And the fact that flag X bullet, we have proved that it's a two-seagull object, then one can prove that then, because we use some properties of this map Q bullet, then GRX bullet is a two-seagull object. I wrote that it follows from two-seagullness of flag of X, but it's not completely fair. There is a little bit more work to do, but it's true. So now the factorization. So we want to show that this Grassmannian as this Grassmannian simplicial version of the flag Grassmannian as a factorization property. So the way we do it, we observe that in order to define the flag Grassmannian at level 2, we have used pullback of the flag Grassmannian level 1 along the union map of flags. But we may have also chosen to define another version, another 2 level, which I denote by GRX2 tilde, by taking a pullback along the projection of from flag X2 to flag X times flag X, which just first take the first flag and project, and then the second flag and project. So the existence, which is a previous theorem, of the projection map from delta 0, delta 2 to from GRU X2 to GRU X times itself implies that there is an induced map between our version, so the version that we define for GRX2 and this GRX2 tilde, which is where you take the pullback with respect to different maps. And the factorization property, if you remember, would be that this map is an equivalence. If you remember by analogy the Beilinson-Drinfeld case, then in fact this is true. And I chosen to present it as in the run case. So the fact is that these squares are both Cartesians, the square I wrote, which are, if you substitute GRX with the Beilinson-Drinfeld Grassmannian on a curve and flag X with the with run space, then this is exactly the same formulation. And I guess I should stop at 11:20, right? For questions.
Yes. Yeah.
Okay, thank you. So the proof is just, as you can imagine, I mean, the projection I mentioned before that are given from the previous theorem gives you a map from the Grassmannian of the union of two flags to the product of the Grassmannian of the two flags. And you have to prove that this map, which exists, you know it exists, it's an equivalence. Okay, and yeah, and this is how we do it. Let me also say one more thing. Of course, this tilde construction that so if you take this tilde construction grx2 tilde, this again gives you a two truncated simplicial object. Okay, so you can extend it coskeletally, and you get like a grx tilde ballet, so a simplicial object. And the fact that is that this isomorphism between grx2 and grx2 tilde actually extends to an isomorphism of these two simplicial objects, grx ballet and grx ballet tilde. And the fact that it extends, it's in the Beilinson-Drinfeld case, is the fact that the factorization isomorphism satisfies a cocycle condition on the run C 3 times disjoint. Okay, this is the way we translate it in this context. Okay, then we want to define something like a fusion product using this. So we reconsider the first, so level 2 to level 1, and we split the maps in 2 parts. So delta 1 is the one included in the union, and delta 0 and delta 2 are just the projections. And delta 1 is proper because it's defined as the pullback of the union from good flags to flags, and this last map is proper. And so we can define a fusion product. Here is where we use not only properness, well, in some cases properness is not even needed, but we use the two-signalness property of grx bullet. Well, if these the derived category of L-adic sheaves or of D modules, then there is a fusion monoidal product, which is defined by using the correspondence that is written at the beginning of the slides by pull-push. And the fact that it's a monoidal structure, it follows immediately from the fact that grx bullet is two-sigal. So it's in particular, equivalently, it's an algebraic correspondences. So when you go to sheaves on that, automatically you get by pull-push a monoidal structure. Okay. So let me skip these things. So that in the next 2 slides, I prepared like actions. Of course, there is a notion of the positive loop group, a notion of the full loop group, and there are actions of these guys on the Grassmannian with the fixed flags. Then you integrate over all the flags, and you get loop and positive loop group actions on the flag Grassmannian. This is explained, but it's not really important. It's just that we wanted I wanted to remark that we can do it. And this is the second part of the actions where you integrate over all the flags. And of course, one would like to make sense of the derived category of the modules of L-adic sheaves on X, which are equivariant with respect to the positive loop group version. And also we would like to upgrade the fusion product defined before to an equivariant fusion product. And then of course the daring question is if this can be done, and I believe that this first phrase can be done. Is it true that this monoidal category is Tannakian in some sense? So I think it's at least that's the way I see it. It's very much very complicated stuff. This, and so maybe starting with the same question but fixing a flag like an easy surface like P1 times P1 and D being P1 and Z be empty. I mean, just look if there is a Tannakian interpretation at a fixed flag. But this is in progress, and progress it's a optimistic word. Okay. And so I will also be quick on this. So of course, we can also define an Hecke stack where you just, it's the same definition that we gave before when you fix a flag F composed by D and Z. And this, if you look at this blue part, it's the same definition as the one of the Grassmannian, but here on the left, it's instead of taking the point map into the below by the trivial bundle, we take all bundles. So these guys classify pairs of bundles on X times S, which have compatible trivialization on Y minus D and Z hat. And here it should be Z hat affine, of course, it's a mistake. In this case, this guy is a stack, is no more a sheaf of sets. And of course, this diagram gives a relation with the stack of G bundles, and also with the Grassmannian and the loop group. But this is totally formal. And the nice thing to keep in mind is that, well, it's obvious also, but that the Hecke stack has two projections to the stack of G bundle on X. Okay. And hopefully I will finish with this direction. So I think I try to list everything we might do or people interested could do, but of course there might be other things. So the first thing that Guglielmo Nocera is pursuing now is to reinterpret the fusion and convolution product in the curve case using this flag approach for the curve case, so using Cartier divisors. So basically putting forward the remark by Belinson-Drinfeld. Then you might have noticed, I mean, somebody might have noticed that there is no derived geometry in this case, in the description I gave. And this is mainly because of laziness from our part. So, and so this can be done, but for example, one interesting thing in this extension is you might have two way of saying what a derived flag is. So it could be a classical flag on the truncation, or it could be like fully derived flag. So like D virtual Cartier divisor, Z an element in the derived Hilbert scheme, which is contained in that. I mean, I'm pretty confident that taking classical flags on the truncation, I mean, all the results should go through, but the proofs are not, I mean, they should be adapted. About fully derived flags, first of all, I don't really have a precise definition of fully derived flags, so it might be a heel-posed question, but even if one come up with something reasonable, I'm not sure that the two things are the same. So there might be two derived versions to consider. Then, of course, when you introduce the Hecke stack, so by mimicking what's happening in geometric Lagrange for curves, I mean, you have a correspondence from this flag Hecke stack to the stack of G bundles on the surface X, and now if you choose a class of sheaves, of elliptic sheaves or D modules on the stack Hecke, on the flag Hecke stack, then you can consider the usual So you pull back, you tensor with this sheaf, and then you push forward. So like a Fourier-Mukai. So you choose a class of kernels, and maybe this class of kernels, like in the geometric Langland case, could come from the Grassmannian, which is inside the Hecke stack. But I mean, this is super formal in the sense that we can do it, but the essence of one of the key points of geometric Langland for curves is just that the choice of these kernels, it's important. So it comes from, for example, from geometric Satake, and so yeah, I mean, it's just something we can do. But the real point is how to choose these sheaves in a meaningful and moreover interesting way. I already mentioned the geometric Satake problem at a fixed flag, so I will skip it. And another question coming from classical geometric Langlands is the fact that you have a forgettable map from the flag Grassmannian to the stack of G bundles on X. And suppose you can prove that the fibers are, let's say, the RAM contractible. And then this shows you that the pullback along this map on D modules, say if I take the RAM contractibility, it's fully faithful, which is an important thing to be used in the geometric Langlands for curves. And here we can ask the same question. I mean, the way it's proved in the geometric Langlands for curves, it's this theorem by Gates-Corey, which is the space of rational maps is contractible. So the fibers are isomorphical to the space of rational maps. So we can try to define a space of flag rational maps and see if it's contractible or not. Then there is this higher dimension. I will be quick because I'm over time. So what about, you might ask, what about dimension so we moved from curves to surface, what about if I move to trefolds and higher dimension? Well, our construction is, you can iterate our construction. So suppose you have a flag D, it contains Z2, and then it contains so on and so forth, ZK. Then you can consider the Grassmannian by saying that the Grassmannian is bundles on X times S, which are trivialized outside D, on Z2 hat minus Z2, Z3 hat minus Z3, until ZK hat minus ZK, compatibly trivialized. But the problem is that if you, this is something you can iterate in higher dimension, but the point is that oh, I didn't mention the theorem. It's yeah, Hartog's. By Hartog's theorem, I mean, this is exactly the same construction that we defined. So it's the same thing as bundle on the whole space, trivialized outside D and on Z2 hat compatibly because of Hartog's theorem. So okay, one can say, okay, well, we can think about two things. For example, modify the definition of the flag Grassmannian, or moving from G bundle to G gerbs, where maybe well, these choices in such a way that these choices could maybe make the contribution of flags of length bigger than 2 appear. And this brings to replacing G bundle with G gerbs, and this is a project that was begun by Binda and Porta, and now it's probably taken by Nocera. And the only open part is formal gluing for G, let's say for G gerbs. And the rest, the flag Grassmannian and all the factorization results should have the same format as the one described in this talk. So, so even in higher dimension, this setup could be useful. Thank you for your attention and congratulations to Michelle.